Hello class, I'm here to talk about chapter 7. I did record a video last night that I deleted. It was late. I was having a lot of problems with my computer. Many things had changed. I have lost many links and tables. So I decided just to record a new video and make some observations. One of them is problem 48 and 50, it relates to exponential. We're not going to be covering exponentials, so you are not required to complete a 48 and 50. Um, and I have mentioned, I had assumed the problems 22 to problem 30 without really look much into it would be for the CLT for the simple means. And in truth, from problem 8 all the way to 30, we always going to be using the formulas for the CLT for sums. The problems for CLT for simple means does not start on your homework until problem 61. Since I have not previously assigned anything above problem 50, I am not going to be changing anything, but I will go over a little bit on the simple means in case you do have a question on your midterm. We are going to focus mainly on the CLT for the sums, but you could be presented with some questions. For example, how would differ the formulas for the CLT for simple means from the formula, I can't remember exactly. Oh, there we go. How would the formulas from the CLT for the simple means, how is it different from the formula for the CLT for the sums? Well, first of all, the central limit theorem or the CLT, it's pretty much the definition I like the best. It's just the CLT tells us exactly what the shape of the distribution of means, the shape of the distribution of means will be when we draw repeatedly samples from a given population. Specifically, as the sample is going to get larger, the distribution of the means calculated from repeated sampling will approach normality. I did post a video today in your discussion thread, and I'm just gonna play quickly this part right here to see if you can understand the definition I just gave you.
Let me show that to you another way. Let me draw back in that bell curve, the population bell curve, and with a population mean of mu. The sample mean is x bar. We need to make an adjustment because the sample mean is not the same as the population mean. We have an error. So if the sample size grows and grows and grows, or I let it grow doing more sampling, the error gets smaller and smaller until eventually there's no error. The means are equal to each other. And again, no adjustment is necessary.
So please take a few minutes to watch this video. It also talks about t-score, t-distribution. You're going to be exposed to different score besides the z-scores, and you're going to wonder what that n minus 1 means. And this is what this video is about. And it shows you a table when you calculate it with just this simple size, and then when you just subtract 1 to divide, uh, you're gonna see how the difference increase. So it's really trying to make that difference more significant for us to analyze all this information. Okay, so we're gonna be going over the problems that makes to make more sense. And again, it's always gonna be about it. In this case, from problem 8 all the way to problem 30, it's gonna be about the central limit for sums. And I have posted here, or I have pasted here, the formulas that you find on your book on page 422 on the book, 430 if you put it over here. And here are the formulas. It's telling you if this CLT for sums, the formulas, and this CLT for simple means. When would you use this CLT for simple means? Well, all the problems here, you're gonna see they all refer to find the probability, the sum of some values, and here's also where's the mean of the sum of the values. However, if you go to your book, this is where you lie the confusion for me, because the first part here shows the simple means of average, then section 7.2 shows the central means, um, the COT for sums, the ones I assign is actually showing you the COT for sums first, and then a beginning on problem 61, then it started COT for simple means problems, which I have not assigned any, but I do want you to take a look at the formulas in case I ask you. For example, right here is telling you the COT for simple means, which means if you go back to the beginning of the chapter, is ask when you ask if, the probability that the simple mean is between 85 and 92. So right here, you're giving two values, and then you're trying to find the probability of this, the mean between these two values. Then you would be using the COT for simple means. However, if you go to the COT for sums, you're always gonna be asked the probability for sums. Let me go up here. Actually, let me go down. You'll be asked for the probability that the sum of some values, or the how many standard deviations are above or below uh, the mean of the sums. Then you're going to be using the COT for sums. We're not going to be covering the COT pocket change or the cookie recipes. We're not going to be covering that. Okay. However, I do need you to take a look at the formulas. Right here, what I was going to show you is what this all means. If you recall from problem from chapter 6, so this crazy formula, which I can put it down here. So this crazy formula right here is just the COT for sums is represented by the CLT for sums of a normal distribution. So it's telling you about the sums of the values for a normal distribution. For your for your mean, you're gonna have to multiply the sample size n by the mean of the population. And when I say population, I'm not referring to the population of the world. I'm talking about if you're in the classroom and there are 50 students, that's your population. Okay, and if I take a sample of 40 students, that's the sample of your population. So the sample size times the mean of the population. And for your standard deviation, we're going to have to do the square root of the sample size times the standard deviation of the population, which I have put in here. The mean of the sums, it's going to be the sample size times the mean of the population. The standard deviation of the sum is going to be the square root of the sample size times the standard deviation of the population. Once we have defined this, it's going to be exactly as this value. The mean is going to be this value, mean, and the standard deviation is going to be the same as this value, and we're going to be able to use this formula, which if you go back here, which I actually have put it down here, z for the simple mean, the sum of x minus, so it's actually my x value that we had it before, minus this sample size times the mean of the population right here, which we're going to define is the mu, and divided by The standard deviation is the square root of sample times the standard deviation of population. Right here is my standard deviation. So all this here is the same as this, but we first need to define these values in order to replace on this formula. So again, mu, let me make sure I put it here, mu, and then standard deviation, and so this that you're looking here is this, and then the standard deviation is this. Wait. Okay, so right here, the top, and right here, the bottom. And my x is going to be the sum of the values. Find the probability that the sum of 95 values. That's what it means. The sum of the values right here, which is going to be the same as my x. So my x is actually the sum of values. So all this here are these formulas, which we're going to be using for all these problems. Okay, so it's important that you go over these formulas to understand what they're asking. So now that we have defined all this, we can go back here, go over quickly here. Has a mean of 80 for the whole population, okay? A standard deviation of 12. A sample size of 95 is drawn randomly from the whole population. It's not telling us what is the population, but it could be anything. So a sample size 95 is going to represent the whole normally distributed, the whole population. Sample size is 95 times my mean. So we actually found the mean for our whole distribution, which they took right there. So see 76. So the sum of 95 values that they got it is 7,400. But the mean of my whole distribution right here is 76, actually for the sample. Okay, so now let's define the standard deviation. My standard deviation is going to be the square root of my sample size, n for sample, times my standard deviation for the population, which is I have put whole numbers to be consistent since the whole problem is referring to whole numbers. It adjusted for me because I have previously put the formulas. If you remember, the mean goes in the middle, and then you do one standard deviation below the mean. So 7,600 minus 117 because it's 1 times 117, and then minus 2 times 117, so far so on. And then for above or positive, you're going to do the 7,600 plus 1 times 117 plus 2 times 117, so far so on. And that's how I got these values right here. So problem 8 is asking for the values that is less than 7,400. 7,400 is going to be about here. So you shouldn't have, you're just going to have this area right here. If we would shade this area, it should not be, I'm not going to insert a shape. I don't want to confuse you. It should not be a large area. Okay. I just, this, I put the average of both values, and then you're going to see why soon. It's going to help you. Okay, then now we found the mean of the sums that is going to represent the mean of my whole population. We found the standard deviation of the sums, which represents the standard deviation of the whole population. And now we have our value of x, which is the sum of all values. These are all values that you're going to be putting on your z score calculation that we have done several times on chapter 6. So I can just put it here. So we're gonna have to find the z-score first, which is gonna be your x value. Remember the x value, the sum of all values, minus your mean divided by your standard deviation. And then you got a minus 1.71. So it's telling you that this value that we're looking for less than 7,400, it's about right here, 1.71. And if you see that the middle between -1 and -2, the average of these two values, 74.25, and it's supposed to be 7,400, so that's about right, minus 1.71. We're gonna have to refer to we're gonna be getting your z, and then we're gonna refer to the z table that we use so many times on chapter 6. So we found the z value of minus, this is your z value. Okay, don't confuse with the mean of the sums. Maybe I should put it in another place. Maybe I can put it down here and put my z-score so you know what I'm referring to. So my z-score, it's going to be minus 1.71. So minus 1.71 minus 1.7, and then the column 0, 1 is 0.0436. So my percentage or my probability is 0.0436. Let me check, double check. That's correct. What does that mean? It means that the probability that the sum of the 95 values is less than 7,400, it's 4.36%. And if you ask yourself why I have not subtract from why I have not subtract from 1 from the whole curve, is because I just wanted this little portion right here. I'm not calculating from a value up here down. I'm just using this little portion, which is minus 1.71 below. So we would be done with problem 8. And then problem 10 is asking you find the sum. So I should put answer 8. And maybe I can move this a little down, and I can copy this over here. So now we're going to be calculating problem 10. Find the sum that is 1.5 standard deviations below the mean of the sums. So we're asking for a value that is 1.5 standard deviation below, therefore negative. And that's when I said this will help you. If you would do an average between the -1 standard deviation 2, you would get a 1.5, and your value would be the sum of these two divided by 2 is 74.25. To confirm that, we're going to go over here and we're going to do equals to, what is your mean? 7,600 minus below the mean 1.5 times your standard deviation. So you're doing 1 times 117 and then half times 117, and you should find a value that it should not be a percentage. Actually should be just a regular number of 74.24.56. If you put the digits, or you could just round up, and there we go, we'll have the same value. We're going to be doing the same thing for problem 12 for the rest of the problems. So right here, also assign one that is less, which I could have assigned one that is greater. You just know that it just changed depending where you're calculating the z value. So let's start with the distribution of results from a cholesterol test. Has a mean of 180, so your population mean. 180. Your standard deviation of the population is 20, and your sample size drawn is 40. Okay, and then find the probability that the sum, problem 12, find the probability that the sum of 40 values is less than 77,000. So the sum of the 40 values is less than 7,000. Now we're going to find the mean of the sums, which is going to be the sample size and times the mean of the population. There we go. So now we have the mean of the sample, which is represented right here, and it's going to just, when I do the standard deviation, it's going to subtract 1 times, 2 times, 3 times, 4 times, and add 1 times, 2 times, 3 times, 4 times. So the standard deviation of the sums, it's going to be the square root of the sample size times my standard deviation. It's 126, and he adjusted here for me, including my average over here that we used it before. Define that, if would be a regular normal distribution like we did on chapter 6. We just have defined that the mean would be 7,200, the standard deviation would be 126, or the mean 7,200, the standard deviation 126, and the x value would be the sum of my values, which is 7,000. So now we have all the values to plug into this formula. Which now I can define my z score, since I have all the values equivalent, my mean right here, my standard deviation over here, and my x value over here. Okay, so we're going to do equals to my x value minus my mean divided by my standard deviation, which we have found a value of 1.59. Therefore, if we go to our table now, so we found the z-score, right? The z-value. So let's go to the table to look at the percentage. So the z-value is 1 minus 1.59, so minus 1.5 right here, and then 59 all the way over here, which is 0.0559. So 0.0559. So your percentage would be 5.59. So the probability that the sum of the 40 values is less than 7,000 is 5.59. Okay, and now we're going to be doing the percentage, actually 14, find the sum that is 1.5 standard deviation below the mean, so minus 1 standard deviation. Well, remember I average right here, because if we do an average between 1 and 2 standard deviation, then that's going to be my 1.5. 1 plus 2 is 3, divided by 2 is 1.5. And if you average the values equivalent to, then is this value right here. And to confirm that, I'm going to do equals to my mean minus, because we are asking for 1.5 below the mean, minus 1.5 times my standard deviation, and then we would find exactly the same value. The next video, I'm going to be finishing problems 22 to 30. Okay, thank you.